Hello everyone. Today we're going to talk about challenging problem for and draw energy grade line and hydraulic grade line with minor losses. Let's see what is the objective. Before we talk about objective of today's lecture, we're going to talk about what we learned so far. We learned about Bernoulli's equation. So the first term is pressure head. The second one is velocity head. Most of the time, we have um, turbulent flow. So alpha 1 is almost 1, and similarly for alpha 2 is almost 1 or 1.05. The next item we have here is the elevation head for pump, and head loss due to friction. We usually calculate head loss due to friction from the equation that we had, but for the head loss, we usually calculate the total head loss, including major loss and minor losses. So major losses comes from Darcy equation. Darcy equation tell us the major losses. It depends on coefficient of losses that we can find from Halland equation or from Moody's diagram, which is the topic for next lecture. It depends on length, diameter, and velocity head. For minor losses, it depends on KL value. KL value is minor loss coefficient. It's manufacturer dependent, so we don't have to calculate. Just we need to use table from your textbook. So this one comes from table in your textbook, and friction factor comes from Halland equation or Moody's diagram. All right. If the diameter is the same, we can factor velocity head and then write the total head loss. All right. So that's all we learned so far for internal flow. Today objectives is understand the impact of pump or turbine on EGL and HGL. So we're going to draw energy line, grade line with the pump, apply partial head loss, align the piping system, and work more with energy equation. All right. So today is just solving an example from energy line and hydraulic grade line. You've done the lab memo for this experiment, so you're already familiar with what is energy line and hydraulic grade line. Let's see what is the problem and what we need to find. In a firefighting system, a pump leads to a nozzle as shown below. A, the flow rate when the pump develops a head of 80 feet if head loss for 6-inch diameter pipe is 5 V squared over 2G, and head loss for 4-inch diameter pipe is 12 V squared over 2G. So from here, we know, okay, the head for pump is given, and this is 2 head loss for different piping diameter. In the picture, you can see we have 6-inch diameter and 4-inch diameter, and also the nozzle has 3 inches diameter. All right, so what we need to find is a sketch energy grade line and hydraulic grade line. Find the pressure head at suction side of the pump. All right, so find the suction head, pressure head at suction side. What is the pressure head? Pressure head, you know, it's not P, it's P over gamma. So we want to know what is the pressure head. What is the suction side of the pump? So in each pump, we have two sides. One side is this part that we call it suction side. So this part is suction side of the pump. And the other side after the pump is discharge side. Okay, so we want to know what is the pressure before the pump. All right, then what's next? Find power of the pump. So we want to know what is the power for pump, or W dot. We have equation to find this one, right? Find the power of the jet. We also need to find the power for the jet. All right, let's see how to solve this one. All right, in this problem, we don't know velocity and we don't know the flow rate, right? For energy equation or all head loss, we need to know velocity. Even the head loss expressed by velocity. So we don't know what is velocity here at 3 different diameter, and also we don't know Q. Once we have one of these velocity or Q, we can find the other one from continuity equation, right? Think about how we can find, because it's not only one velocity, it's velocity at 3 inch, it's velocity at 4 inches, and it's a velocity at 6 inches. The Q is the same, but the velocity is different in different diameter, right? So think about how we can find velocity. All right. Let me see. There's not any way to find velocity at the 3 inch diameter, at 6 inch diameter, and also 6 inch diameter. The only things that we can do, write the continuity equation for all 3 different pipe, and then write the velocity V4 based on V3 or V6 based on V3. So this way we can reduce the number of unknown, right? We can reduce the number of unknowns. So usually in this type of problem, we have a lot of unknowns. So it depends on us how to use all this equation we know to solve this problem. All right, so we know everything's based on V3. So the velocity here is V3, velocity at 4 inch, V4, we know V4 is 0.563 V3, and V6 is 0.25 V3. It's like kind of we know what is the velocity. All right, what is the next step? After I know velocity, what I need to find for the first step is to draw EGL and HGL. How to find EGL and HGL? We know from previous lectures, EGL is pressure head plus velocity head plus elevation head. And if we just subtract velocity head, we have hydraulic grid line, right? So we need to know what's the pressure, we need to know the elevation, and we also need to know velocity. For velocity, we just know the velocity based on V3. We need to find some way to find the pressure, because elevation is also given. It's 50 here, 50 feet, 70 feet here, and 80 feet here. All right, so the only things that we need to know is pressure head. How we can find the pressure? Yes, correct. if you write the energy equation between 2 points that we know a lot in these 2 points, we can find the pressure. Which point is a good point to write the energy equation? Let's call this at A, let's call point 1 and point 3. Why these 2 points are a good point to write energy equation? Because we know it's open to atmosphere, so pressure at point 1 is 0. We know it's a large surface, so velocity at point 1 is 0. And we know the elevation. If I assume the datum is right here, so my elevation is also 0. Similarly, I can think about what I have in point 3. P3 is 0 because it's open to atmosphere. Velocity at point 3, I don't know. Z3 is 10 feet because here is 10 feet, here is 80 feet, so elevation is 10 feet. Go ahead, stop the video, write the energy equation between point 1 and point 3, and then see if you can find velocity. All right, let's write the energy equation. Pressure at 1 plus V1 plus elevation head for pump equals to P3 plus V3 plus Z3 plus head loss. If you have a turbine, we can write. Okay, now it's time to think about what is 0. So this one is 0, it's open to atmosphere, large surface, elevation is 0, we don't know head for pump, pressure at point 3 is 0, velocity at 3, we don't know, we know the elevation. There is no turbine, but we have some head loss. All right, let's see what we have and what we don't have. It's 0 plus 0 plus 0 plus head pump equals 0 plus velocity at 3 square over 2g plus elevation, which is 10 feet, plus head loss. What is the head loss? It says for 6-inch diameter, we have some head loss. For 4-inch diameter, we have another head loss. All right. So let's see what is the head loss. In the problem, it says the head loss in 4-inch is 12 V4 squared over 2G plus head loss in 6-inch diameter pipe is 5/6 over 2G. So this is all the head loss, okay? So this is head loss in 4-inch and 6-inch pipe. All right, so from here, if we solve, the only unknown we have is V3. Why? Because we know what is V4 and what is V6, right? So it's the head for pump is 80 equals to V3 squared over 2G plus 12 plus 10 plus 12. What is V4? It's 0.563 V3 squared over 2G plus 5. What is V6? Is 0.25 V3 squared over 2G. From here, I can solve for V3, which is 29.7 feet per second. All right, I have V3. From continuity equation, I can find V4 and V5, right? Let's see what's the flow. How I can find the flow rate? Flow rate is VA. I know velocity at 3-inch diameter. I also know the diameter at 3-inch, so I can find the flow rate. So it's the velocity is 29.7 feet per second, and the area is pi, the radius is 1.5, the diameter is 3-inch, so the diameter is 1.5, it's inch converted to feet, and from here you can find the flow rate. What is the flow rate? Is 1.458. Don't forget about unit. All right, now we have the flow rate and the velocity head. So with having velocity at different diameters, so I know the velocity at 3-inch diameter, I can find the velocity at 4-inch diameters and also 6-inch diameter. So I also can find the head loss, because if I know the velocity, I can find the head loss. What else I can find? The velocity head, right, for all these three different diameters. Right, let's go ahead and find the head loss. Stop the video and find the head loss and velocity head. All right, let's find out what is the head loss. Is 6-inch diameter pipe is 5v6 squared over 2g, which is 5v6 is 0.25 v3 squared over 2g, and I just find what is v3, which was 29.7 squared over 2g, and g is in British system, make sure you put 32.2. So from here, head loss is 6-inch diameter is 4.28 feet. You know the head loss unit is always length. Similarly, you can find for 4-inch diameter is 12 v4 squared over 2g, which is 12.563 v3 squared over 2g, 12.563 multiply 29.7 squared over 2 multiply 32.2. From here, head loss in 4-inch pipe is 52 feet. You can compare the head loss in 4-inch diameter and 6-inch diameter. You can see we have less head loss in the shorter pipe compared to the longer pipe. And also the elevation causes a lot of head loss. All right, next step is to find velocity head, because we need all these things to draw energy line, grade line. Velocity head. So let's find out what is the velocity head. Velocity head for V3 is 3.7 feet. For V4 is 4.33 feet. If you just substitute the velocity for each pipe, V6 squared over 2G, is 0.856 feet. All right. All right, so it looks we have everything that we need to draw energy line and hydraulic grade line. All right, let's go ahead and find out how to draw energy line and hydraulic grade line. All right, stop the video and try to draw energy line and hydraulic grade line. All right, here is where we want to draw hydraulic grade line and energy line. So if you want, you can draw a table and see what you have. For example, you need pressure head, velocity head, and elevation head, right? So for point one is here, point 3 is here, and so from point 1 to point 2, let's call the pump point 2. We have some head loss, right? So here we have some head loss in 6-inch diameter pipe. Then again, we have some head loss in 4-inch diameter pipe, and then we get to point 3, right? Okay. So for pump, we know what is the head for pump. So it's just head for pump is 80 feet. We know the head loss in 6-inch diameter is 4.28 feet, and we know the head loss in 4-inch diameter is 56 inch. So for the pressure, for the velocity head at point 1, because it's a large surface, velocity is 0. At point 3, we find pressure, velocity head 13.7. All right, for point 1 and point 3, pressure head is 0. What else we have? Elevation at point 1 is 0 because we assumed our datum is here, right? Here is our datum. And at point 3, the elevation is 10 feet. Okay, that's all we need to draw energy line. So energy line at the water tank, it's right here. So let's say this color is energy grade line, and then I use another color for hydraulic grade line. Then at pump is the second point, right? So before I get to the point 2, I have some head loss. So what is this head loss? It's head loss due to 6-inch diameter pipe, which is 4.28. So wherever my energy line is, I have a drop because of this head loss. So this is my energy grade line. So due to head loss, I have some drop from where I was. Then I have a pump. The pump gives me 80 feet head. So I go up. Here is head for pump, 80 feet. And I get to this point. Let's go a little bit up, somewhere here. Then if I don't have the head loss, I go all the way like this. But if I have head loss, I have a drop, right? What is this drop? It's 56 feet because of head loss in 4-inch diameter pipe. So I have a huge drop here, head loss due to 4-inch, which is 56 feet. All right, so I get to this point. So that's all for my energy grade line, right? So anytime you have a drop, it means there is some head loss, and in real world we always have some head loss. So it's not like previous example, it's not straight, we always have some drop, and wherever we have pump we have some jump, and then based on head loss we go down. If we need to apply some pump, or sometime if we have more head we can use turbine. So the principle is the same. Let's see how to draw hydraulic grade line. Okay, so let's say this color is for hydraulic grade line. At the first point, everything is 0 and hydraulic grade line is in the same place. After that, the difference between energy line and hydraulic grade line is just velocity head. So I go down, and it's not in a scale, but we know we have a drop, which is velocity in 6-inch over 2g, which is 0.856. Okay, then I get to the pump, I go up, and then I have a drop here. And what is this drop? It's velocity head. It's V4 squared over 2g, which is 4.33 feet. So I get to this point. All right, so this is my hydraulic grade line, and the red one is energy grade line. That's all. So this is how we draw hydraulic grade line and energy grade line for a piping system that we have a pump. Similarly, we can do it when we have turbine. All right, we're not done for this problem, because we still need to find power pressure head at suction section of the pump. So here is the suction side, and we want to know what is the pressure head at this point. All right, what do you think? How we can find the pressure head in suction side? Yes, always write energy equation. What is a good point to write energy equation? Correct. If you write the energy equation between point 1 and point 2, you can find the pressure head at point 2. Stop the video and find the pressure head in suction side, and then calculate the power for pump and power for jet. All right, so we're going to write energy equation between reservoir and suction side. It's P1 over gamma plus Z1 V1 plus V1 squared over 2G plus Z1 plus head for pump equals P2 over gamma plus V2 over 2G plus C2 plus head for turbine plus head loss. Let's think about what is zero in this equation. Okay, at the surface of the reservoir, pressure is zero, velocity is zero. If I assume the datum is the surface of reservoir is zero, how about pump? Do we have a pump before the suction side? No, we don't have any pump in the section side. So this one is also zero. The reason is no pump before the suction side. So this one is zero. Pressure at point 2, its suction side, I don't know, this is something I'm looking for. Velocity at point 2 is the same as velocity in 4-inch diameter, 6-inch diameter pipe. Elevation, I know the elevation, there is no turbine. And what is the head loss? Head loss is only due, this is the important part, head loss is only due to 6-inch pipe. So just consider the head loss for 6-inch pipe. All right, let's substitute the number and see what we get. 0 plus 0 plus 0 plus 0 is equals to pressure at suction side plus V2, velocity at section side is 0.25 multiply V3, which is 29.7 squared over 2G minus 20, the elevation is minus 20, plus 0 plus head loss is 5.25 multiply 29.7 squared over 2G. From solving this part, we can find the pressure head, which is 14.86. What is the unit? Is legs. So this is pressure head in suction side of the pump. Right. What is the next step? We want to know what is the power for pump. So power for pump is, or in your textbook, W dot is gamma Q head for pump. What is gamma for British system is 62.4 multiply Q, which was 1.458, and the head for pump was 80 feet. If I want to convert it to horsepower, I can divide it by 550 to convert it to horsepower. So power for pump is 13.23 horsepower. How to find the power for jet? It's the same equation. So power for jet is gamma Q and head for jet. Gamma is 62.4, flow is 1.458, 62.4 multiply 1.458. What is the head for jet? It's only velocity head. So everything in the jet is velocity. So divided by 550 to make it horsepower, and P for jet is 2.27 horsepower. So the only tricky point in this problem is you need to know the head in the jet is just velocity head. Head for jet is velocity head. It means at jet, all the energy convert to kinetic energy. All right, let's call it a day. I have a homework that is similar to this lecture, so you repeat this lecture with different flow or different velocity or head loss. Let's call it a day, and next topic is iteration method that is in your quiz. Okay, have a good rest of the day.